Right, today we're picking back up on railroads. We're going to talk some more, finish off the piece about track, and talk about some geometrics on it as well. We're going to start off with a little bit of, I guess, freightness, and looking at how freight movements in the U.S. and how much it costs and where freight comes and goes to. Kind of ties in with the railroad piece, right? Since we've talked about some of the other modes, particularly cars. It's kind of interesting to see how this fits. All right, so this is couple of news articles I found over the years. This is about passenger transportation. So this is an idea of how much energy each mode of transportation uses. And they're divided by passenger miles traveled. And so it's BTU per passenger mile traveled. It's an odd unit, right? British thermal units per passenger mile. But the point being is versus how many passenger miles traveled on each mode of transportation, and then dividing that by the total number of BTUs, or actually, I guess the other way around. But it's a unit of energy per passenger mile that you were able to move someone. And what they're probably actually looking at is how many, like on a train, how many passengers were on the trains times. If you had 100 passengers and you went, 30 miles, then you would have 3,000 passenger miles, right, for that. And then however many BTUs it took to move the train that far, that's how you would calculate that for that. If there's empty seats, it still may take quite a bit of energy to move the train. Like if the train was completely empty, it would take quite a bit of energy to move it. And so that hurts your mileage, that hurts your efficiency, right? And I think that's kind of what's hurting the transit buses, because they're not often full for this calculation, right? So a bus isn't that much of an energy hog. It's just that it has a lot of empty seats a lot of times. How's that? Like a commuter train is quite often near full. Hopefully they try to get them. Passenger trains, somewhat too. How often they stop is going to affect how much energy they use as well. So here's just a breakdown. Obviously this is produced by Amtrak. Actually it's an energy data book, but Amtrak, I think, is very happy about this. So they have the lowest energy use per mile. Air travel is not much higher, right? And if you think about that, once you're up at 30,000 feet or more, there's very little friction, right? So the efficiency at that point becomes quite good. Now, lower elevations, they burn up a lot of fuel, and they burn up a lot of fuel just taxiing back and forth. We saw that graphic last year in air transportation design. About 10% of their fuel load is just moving around on the ground. It's pretty inefficient movement there. Once they're at speed and up at altitude, there's very little friction. That's why they fly so high. That's the only reason they would fly so high, is to reduce that drag and get that efficiency there. So it's kind of interesting. I wouldn't have thought that. For a commuter rail, not as efficient, probably because they make so many stops. And on the inbound side, like if you're riding the South Shore from Dune Park in, it's near capacity in the morning. If you're on the outbound, those trains have to return back out to Michigan City every night, or during the day even, to run again. And so those return trips are very there's a lot of seats being moved and not many passengers in it. So it's probably hurting commuter rail to a degree. Automobile, we didn't really expect that to be great. Personal trucks are even worse. And you just think about the miles per gallon. That's it kind of tracks with this BTU per passenger mile in that. And then the transit buses is the worst. That's like a city bus. Right there. I read once if the most efficient form of transportation is actually a 15-passenger van, if it's near capacity. If you've got 14 or 15 passengers in it, that it's one of the more efficient forms of transportation. I don't know. I heard that in college. I don't have the data to back that up, but that's one thing I had seen just based on number of people being moved per energy consumed, right? 15-passenger van gets about 20 miles per gallon. So do most pickup trucks. And so you're going from 2 or 3 people in a pickup truck to 15 for the same number of BTUs. Maybe that's how that fits in. And you can compare this with freight mode in waterways. And so you may know this. This is the most efficient form of transportation. This is in inland waterways inside the U.S. or even across the ocean. Shipping by water is the most efficient form. You can't beat it, right? Trains are pretty good, but they're nothing compared to shipping on water. Really, all your you're paying for propulsion, you're expending energy for propulsion, and that's about it, right? And if you're on an inland waterway, the tide or the flow may be going with you, right? For that. And so we've got a pretty extensive network. We've got an intercoastal waterway that goes all the way from starts in Texas and curves around up through North Carolina, I believe, is about actually most of Florida. I'm not sure if it gets in. I don't know about South Carolina. Well, anyway, there's all on the Gulf Coast. There's an intercoastal waterway all the way around along the Gulf Coast, so you don't even have to sail out into the Gulf. They can just run these barges through this intercoastal waterway right around, all the way from Texas through Louisiana up into Alabama. It's all intercoastal waterway, very well protected, heavily managed by the Army Corps of Engineers and taken care of through that. And it's a huge economic motivator or piece along the Gulf Coast, where we have lots of oil refining. A lot of the grain comes down to Mississippi, which is also a regulated waterway by the Army Corps. They have dams and locks every so often to make sure that you can always get enough water in the river so that you can have the draft you need on these barges, right? So here's a comparison. One of these is a barge, right? And they often do a 15 barge tow. And so they lash these together, and then a single tugboat back here is pushing that for that. And that's a 15 barge tow. And that would be, I guess, the standard size on most of the U.S.'s waterways. So you can, in one barge, you can get 1,750 tons of capacity. A rail car is about 110 tons of capacity, right? So a lot more can go into one barge. You're doing 15 barges at a time. You have a single crew on tugboat pushing this, and that's, super efficient, right? That is super efficient, right? And versus a semi, which you can do about 25 tons, right? So that gives you a comparison. Here's in dramatic visual action here, one barge versus 16 rail cars versus 70 semis, right? A 15 barge tow would take 6 trains, basically, and 1,050 semis, right? And then here's, if you wanted to go by length, there's your lengths. I'm not sure we care that much about that. So it's really efficient. Here's the miles, how many miles a ton of freight can be moved with a gallon of fuel. And that's interesting. This is a little bit older data. This is published by the ports of Cincinnati and Northern Kentucky on the Central Ohio. 576, you can go 576 miles, 1 ton of freight can be moved 576 miles with a gallon of fuel. And with a train, it says 413. That number is actually much higher now. It's more like 450, 460. They've added much longer trains than they have, and that number has been dropping, or actually it's going up. It's a good thing, right? It's going up. So it's actually higher than it was. There's very little rolling resistance, obviously, on trains, but you still have to go over hills and stuff like that, and that's going to use up more fuel. And then 155, a 1 ton can go 155 miles on a gallon of diesel fuel. For a truck. So just an interesting, here's comparisons in emissions, and I don't have anything to back this up on. Again, this is coming from the ports of Cincinnati, Northern Kentucky. So obviously freight by the river, traffic by the river, shipping there is got the lowest emissions in carbon dioxide, right, per million ton miles through that. Trains are in the middle, and then trucking. I just thought it was interesting. Here's air quality emissions, picking up on that. Here's carbon dioxide again, CO2. And based on if you drive yourself per passenger mile, now we're looking back at passengers, per passenger miles traveled. Here is the emissions for that. Driving an SUV, driving a car. Here's flying on an airplane, right? This got hit in the news with Greta Thunberg last year about airplane traffic and how inefficient, or how much emissions it produces, how unclean or polluting airline travel is. Well, you're basically burning jet fuel and it's shooting out the back. There's no emissions there. We're not, cars and all other ground vehicles now, even trains, have to have emissions equipment built onto it to reduce pollution. Airplanes got none of that. They're burning fuel. It is turbo. They are turbojets now, so they're not. it's not just lighting fuel on fire and it shoots out the back. They have the turning turbine in there, and it creates a high pressure compression zone and so forth and all that. So it's a little more efficient than just a rocket engine would be. But there's no way to collect that stuff coming out of the back of the jet engine. Well, no way we figured out yet. So yeah, the air quality is not so great on an airplane. Transit bus. Driving a Prius, Amtrak, it's actually a little bit better. Rail transit, this would be more in that, this is in the range of commuter rail, right? But that's a really low number, 25 riders per car. I think about South Shore. South Shore, you can get like 100 people on a car, right? So that's more down in here. And then intercity bus, so look at, intercity bus, finally, all right, maybe their BTUs per passenger isn't great, but their emissions is great. All right, for there. And of course, you can't beat just walking. There you go. And here is, if you add somebody into your carpool or your transit or your van pool, it takes very little extra to move that, right? Adding a person into a van, you're not gonna notice any difference in your miles per gallon. You're not gonna burn any extra gas. So it's a very, very low extra addition. For the emissions. And this was interesting. This was freight tonnage by mode and route. And so this is again comparing highways, which are in red, blue, which is the waterways. And so here's the inland waterway. I guess it does stop in Florida through here, but there's also a little bit along Georgia and South Carolina, a little bit of North Carolina. There's an inland piece there too. Most of it's along the Gulf Coast. And then the Mississippi is the major one. And here's the Ohio River. And coming all the way from Pittsburgh all the way down, the Mississippi continues on up to the Twin Cities. That's about as far as they would, what they classically term navigable waterway, and what barges actually run on. Twin Cities is about as far as I think as they go on that, maybe a little past that. But that's some of the last sets of locks and dams, I think, on the Mississippi. So that's about the extent of the waterway. Here's the Chicago River coming up to Chicago. You kind of gets buried underneath this, but that's coming up through Illinois. That's a pretty popular route as well. That was the shortcut over to the Great Lakes in the old days. Now, not many barges, well, very few, actually come through Chicago anymore to get to it. I think there is a canal around the outside of town. You could still make that route. Through a lot of grain shipping is what it is, and also lots of aggregate. There's a lot of aggregate through here. Here's the Tennessee River and the Tennessee Valley Authority. Has all their dams and stuff on that, but that's all become navigable waterway for major shipping, all right, through that. It's a little California, a little bit. Here's the Columbia River. Here is Puget Sound up in Seattle. So there's a little bit mixed here and there. Other than that, Mississippi is the main one coming down in through Louisiana. And then this is the intercoastal waterway through here. Right, it goes all the way down to Brownsburg. Basically, what's this? Galveston, I think. Here's Houston, so forth. So that's how the freight's moving. Rail is the green on here. So railroads are the green. And you're like, okay, I kind of understand where some of these routes are, right? Here's the Port of Long Beach. This transcontinental route is really busy, right? Hauling containers, mostly container traffic from the Port of Long Beach. Portland has major rail traffic also coming through. And this is the Burlington Northern line through here, the old Northern Transcon route. Whoops. Through that, and I'm back up one. And then there's this. All right, look at this. Huge volumes. This is tons of volume. It's not by value, but by tonnage. Look at that huge volume. What's going on here in Wyoming, right? So, and this has changed. This is not that old of a graphic, but that's coal. So that's 40% of the coal in the U.S. comes from the Powder River Basin, which is in this northeastern corner of Wyoming. And if you've ever driven through what is this one? That's I-90. I think that's I-90 there. If you've ever driven through there, you can see some of this. Almost it's below ground level, but there's a huge generating station. That's what I usually see from I-90 when I drive through. Is huge open pit mining through here, and that's 40% of all the coal in the U.S. comes from there, and it's all transported by rail, almost all, and that's this huge tonnage volumes through here. Now, West Virginia and Kentucky also still produce coal, so does southern Indiana. So some of these routes, this used to be the famous Norfolk Western before it became Norfolk Southern. This is their major coal route going down to Norfolk, where they had exporting sites And that's in the last 2 years, that volume has dropped tremendously and has really hurt them as a railroad. Through that, and coal in general is collapsing pretty much. The number of coal plants in the last 10 years has dropped by half in the U.S. Right? They're not economical anymore compared to renewables. It's one of the problems for that. And so here you can see, here's all the coal-fired power plants being supplied by this Powder River Basin. They go a long way. Right. And not all coal is equal. I think Powder River Basin is a low sulfur coal, and so it's better on the emissions. And if you have to scrub your emissions from your smokestacks, if you're burning coal to produce electricity, you want to start with something that's low sulfur. And I think the West Virginian coal, the Appalachian coal, is a high sulfur coal, if I remember right. So you'd have to have more, you'd have to spend more money on controls and containing that than you would if you were done. So maybe that's one reason so many of these power plants are being provided with coal from Powder River, which is funny because Indiana produces coal, but yet there's power plants in Indiana running off of Powder River coal, not Indiana coal. And you can see, I mean, look at us along the Ohio River here, all those power plants, they're all being shipped by rail over here. This is that line coming across. With Powder River coal. No, interesting stuff. No, I thought so. Maybe you don't. Here's back to railroad track. We left off last time with doing these tie plates and how many spikes you put into tie plates and so forth. Well, moving down, starting at the rail, moving down, now we're down into the actual tie itself. And so here's the tie. Across here, rail sits on it. Then below that is this tie plate, and then it's the actual tie. For that. All right, through here, here's what it looks like. So most of the U.S. is probably still using wood ties for heavy routes, very high traffic routes, and a lot of times routes you don't want to have to do much maintenance to long term. So heavy transit routes, if you have commuter rail lines and stuff, they'll use concrete tie for that. And it's a stiffer tie, and so it actually hurts the ballast more. It'll break off corners on the ballast quicker than a wood tie is a little softer, and the corners of the ballast actually embed in it and help hold it. So a little bit of difference there. So that's the tie. The rocks are called ballast, and this is about a 1.5 2 inch nominal diameter rock, and they're very picky about the rock. They don't want to use limestone because that's too soft, right? If it's a heavy traffic line, they're going to try to use they call it tap rock, or it's like a granite or a schist. So it's a really hard rock, and that's what they use. And railroads are really good at hauling things, heavy things in bulk long distances. So they'll haul their own ballast. They have entire ballast trains. That's what they do is they'll get this tap rock out of the Appalachians or near the Rockies, and then they'll just haul it across the country and use it for their ballast. On again, this would be for a very high traffic line with lots of heavy tonnage on it. You'd want to use that. Now, I have heard you can use limestone on a line that doesn't see that much traffic or lighter traffic. And if it's close and it's cheaper, then it's okay, but you're just going to have to replace it more often. And that's what they do. As over time, this gets fouled with fines, and then it starts, it doesn't transfer load well, and it retains water, which is not good. It hurts your drainage. Your drainage can't flow through it, and so you'll have to come through, and you can completely remove that ballast and put new ballast in. They have entire machines that do that. And there's a link to that at the end of today's lesson for that. So the track design standards, I think we mentioned last time, the FRA, the Federal Railroad Administration, inspects track, make sure it's being maintained well. They do it by different class numbers. And depends on how fast you want to go, how good your track has to be, and what the standards are. They're going to check it for. So here's all the different classes. In the U.S., it's coming up here, most of our Class 1 railroad track is Class 4 track. Freight trains can't go over 60, and what normally, like Norfolk Southern, only their container trains are going 60. Their normal freight trains, like they call it mixed freight, and coal trains and grain would only go 50 miles per hour maximum. The containers typically go 60, and if you watch trains go by, sometimes you get stopped at a crossing out in the country, you can notice that the container trains are going pretty fast, right? So they have a higher speed on them, and they're double stacked. It's pretty amazing, impressive how they go. Passenger train on that, technically it's 79 miles per hour, let's call it 80, right? Would be your maximum speed for that. So there is a speed limit for trains, and for a Class 4 track, then it's 80 miles per hour. Most of Amtrak is going to be running on Class 1 railroad track, which is a Class 4 track. Their maximum speed is 80 miles per hour. So most Amtrak trains, even though technically they could go faster than that, don't go faster than 80. Right. Which is funny because back in the 1920s and 30s, there were 100-mile-per-hour trains, routinely running between Chicago and into Lima, Ohio. So the rail line that goes through Valparaiso out in the country, well, those trains would hit 100 miles per hour or more. The Pennsylvania Central line, early 1940s, they had steam locomotives going 100 miles an hour. Nowadays, we can't go over 80. So there's progress for you, right? Amtrak has a couple of high class tracks, the 7 and 8, and that's for the Excella trains that are running on the Northeast Corridor, and that goes from Washington D.C. up to Boston. All right, so they'll have sections of 7 and 8. That's the only place in the U.S. we've got 7 and 8 class track that I know of through there. And there's some that have been talking about moving up to this Class 6, some busier lines through that. There is some of that really heavy transcontinental route traffic we saw in that one picture going through the Southwest coming up from LA to Chicago. That apparently is Class 5 track. And so the freight railroad there wanted to upgrade the track for it. Somebody who worked for Amtrak told me once that to raise your operating speed 10 miles per hour, it costs twice as much in maintenance to keep to smooth it out and to keep it operating that well. It's going to cost twice as much for maintenance to raise it 10 miles per hour. I don't know if that's true. He told me that back in the late 80s. Maybe it's still true. Maybe it's not. I don't know. Here's Class 1 track, what it would look like. Pretty beat up, right? This is 10 mile per hour track, a little bit better. Here is the main line. This is what most Class 1 railroads are running right now. This looks very standard for a Class 1 railroad, right? You're not going to go very fast on this stuff. And look how bad the ballast is. Look how fouled that is. This has almost no rock left at all. It's just on bare dirt. Not good. Tires are all beat up. You're going to move real slow in that, and the cars are going to rock back and forth as they come across this. You've lost your drainage and a lot of your support. This is so badly fouled. Here's good stuff. You got good ties. They're solid. They're not splintered like this one is, and you've got good ballast in between the tracks. So this will be your 60 mile per hour top speed for freight, 80 miles per hour top speed for passenger trains. This is what the geometric, we talk about how big a car is, and we talk about parking spaces. They're 20 feet long, right, a car, and as your parking space, you aim for 9 or 10 feet wide for that, and a car is, in the range of 7.5, maybe up to 8 feet wide. We've got the max, but it's more in that 7.5 range. So let's look at a railroad car. Now, this is the outline of what that railroad car, this is from the Norfolk Southern, what they say, but they're matching pretty closely. What the ARIMA standards would show for any freight rail line. But this is Norfolk Southern produces this for people who want to build industrial tracks for freight. This is telling you here's the envelope that you need, right? Starting from the railroad, measuring from the top of rail. That's where we measure everything from, right? That's our profile line. From the top of rail, you have to have at least 17.5 feet of clearance. The train car can be up to 20 feet. Up to here, and then they kind of cut off the corners on each side for that, and it's just traditional. That's most cars aren't a big rectangle, right? They go up like that. And if for the road side of it, if you build a road overpass going over the top of railroad tracks, you have to provide 23 feet of minimum of clearance. And so every time you look at doing an overpass, just remember that. Over a road, you only need about 17 feet of clearance, and a little bit less if it's only a collector. Right? But for an arterial, we would aim for 17. We can get away with 14.5, I think, for going over the top of a road. If you go over the top of a railroad, you need 23 feet of clearance minimum. And on either side of the center line of tracks, you're going to need a minimum of 9 foot of clearance either side. All right, so there's your envelope, right? If you need to design around railroad tracks through that. Now, most railroads actually own 100 feet of right-of-way, so they can have multiple tracks in there. But for a single track, you need 9 foot of clearance on either side of it for safe operating of the railroad piece. So that's interesting. The other piece we look at in railroad track piece are turnouts. And so this is what we call turnout, which is how trains change tracks, right? And how they turn. Well, I guess the entire railroad could curve, but if you needed to put a train over on a siding or back the freight cars into an industrial place to offload product and so forth, you're going to need a turnout. And this is what a standard turnout would look like, and they're numbered. And so they have a number for the turnout. This is the number 10. This is a really common turnout, and they go up. Well, they can go up to quite a high number, right? The higher the number, the more gentle the turnout is. The lower the angle. So a low numbered turnout is going to have a really sharp angle and be a low speed turnout. A high numbered turnout is going to be very gentle and will have a higher operating speed to go through the turnout for that. So this is the number 10 turnout. Like I say, it's a really common turnout on most rail lines. Each company will tell you what their minimum turnout number is for what you're trying to do, right, for that. And this is self-guarded fraud. This is for yards, right? So this is if you're switching cars in a yard, you can use a number 10 turnout. You can go, I think, to lower numbers as well for that, but they don't like. The problem with too sharp a one is when you pull a train through a curve, it creates friction, right? Because you're on a straightaway, you have very little, but when you're going through a curve, any kind of curve, it creates friction, which means not fiction. It's not fake. It creates friction, which the locomotive has to pull harder, right? And you may need more locomotives if it's a really curvy track. Turnouts do the same thing, right? It's a curve, and so it's going to create friction. The higher the number of turnout, the gentler that angle is, and the lower the friction value is as the train gets pulled through it, right? So just keep that in mind for there. So that's our turnout. This is what it looks like. This is, if you look at right here, this is where everything is centered off of. Where these rails cross, they call this the point of frog. Here's our point of frog, and that is right where geometrically these things cross. Appears a blow up of it. Right, here's the point of frog. Supposedly this looks like a squashed frog if you ran over a frog on the road. His arms out here and there's his legs. Oh, poor frog. So I didn't make this up. So they call this a frog. This part of the turnout is called a frog. And the point of frog is that geometric intersection of the inside of the rail, of this rail and the inside of that rail. That's your point of frog. It's very close to that. This is what a frog looks like, on a turnout, and this is that point of frog right there. That's your point, right? So if you're going straight through, right, there's a switch up here is moving which rail you're on. That'll switch you from one rail to the other, and then the other side. All right, so this rail, let's look at this one. This rail is moving and getting switched, actually, both of them. So if you get switched over to this track, you come across where it would cross the inside of each route, inside rail of each route. That's that frog. That's where this piece is. All right, so the switch is back here. Here's this point of frog in a turnout. And the angle, this angle here, and you can kind of see at so much distance measured off here, that's where we can set up what the frog is for that. This at a high numbered turnout, this angle in here is going to be lower. This is going to be more of an acute angle. At a low numbered turnout, this will become a larger angle in here. So this is what the frog looks like. As you can see, if your wheel was running along here, it can pass over here. It'll bump, right? You'll feel it. If you ever ride Amtrak or train, that's when you feel the bumps. It's probably you're going over one of these. Most of the major bumps now are caused by this. And the car will often sway and shoot back and forth a little bit, rock back and forth as you go across those. Here's usually Paul Foster from DLZ comes over and does the railroad lecture for us because he designs railroads for DLZ over in South Bend. They couldn't make it this year because we're virtual, but this was from previous years, and I thought he did a nice job of laying this out. So thank you, Paul, for this slide. If you want to work with trains and don't want to leave the Midwest, check out DLZ Indiana. I think they're always hiring over there. So here's where the switch point is, right? And so you've got the switch over here, and then here's that frog. All right, so if you switched, this rail slides over, touches that one, your train wheel comes across, catches that, and follows it around, goes through the frog and goes into here. All right, so that's how these are laid out, and these are turnouts again, right? You can see this is a number 20 turnout, and so this is an even more gentle one. All right, so this is a mainline one for that. Here's the angles, and so you can see a number 10 turnout has a 5 degree 43 minute and 29 second degree of change, right, it's going through here, which would be kind of the angle you'd measure at the frog. And a number 20 turnout is about half that. All right, that's 2 degrees 51 minutes. Maybe they're not quite half for that. So that's a number 20, much gentler. All right, through there, here's the point of intersection, theoretical point of intersection in between the tracks for that point and switch back here. Right, so that's our turnout numbers. Keep that in mind through that. Now let's talk about horizontal curves. I mentioned this when we did horizontal curve stuff, both in 252 and 354 this year. So in case you forgot, right, in highways we measure along the arc. We were going to measure along this. We're going to measure along the arc. We're going to follow the arc of the curve around it. In railroads, they measure it by the chord, and so they're going to break it up into chords. And so this is measuring along the arc, right, in the red. That's how we would measure it in highways work. So our equations for highway horizontal curve stuff is based off of that. They are not equivalent. Don't use highway equations for railroad stuff. Ooh, that sounds like a good final exam question. All right, so are you using the right equations for highways versus railroads, right? And so in railroads, they break it up into equal tangent or equal chords of 100 feet. And they measure it by how many, measuring along those chords, they measure it along. And if you've got an odd number of, not in even 100-foot stations, then there's a residue here. It's 100, 100, 100, 100, 100, and then 41 feet or something like that would be that last piece. But that's how it's defined off of a 100-foot chords, right? And the reason is in the old days, when you were laying out railroads, this is the late 1800s, right? It was when most of the railroads in the U.S. were built. The way you design railroads and lay them out is super easy to do in the field. And it's because they did a lot of this in the field. They didn't actually come back and design stuff in an office. They had a survey party working a few weeks ahead of the main track gang. And then the engineer would come through, or engineers, and lay stuff out right behind the surveyors and or work in conjunction with them, right? And going across the western U.S., none of that they could go anywhere they wanted. They were being given the land for free, and so they would lay out the railroad, and then later the government would just give them what property they were on. They didn't have to pre-buy anything, so there was really no design. It was very quick, very fast design work in the field. And so all of this layout stuff is, kind of think about it, it's really easy to do in the field, or would be the easiest way to lay stuff out in the field. So what did they have? They had a 100-foot long piece of cord, right? And that's it. They literally have a 100-foot long piece of, I don't know if they used metal tape eventually in surveying, but who knows what they started with. But they have this thing 100-foot long, and they'll just lay that out, right? And they stake every 100 feet, and that's enough. That's enough to figure out where your curve is, and then the track crew comes in and puts the curve in and matches where those stakes are along the center line. And that's it. I mean, that's how they designed a lot of the railroads in the U.S. for that. So you've got a 100-foot long piece of cord, and you have a transit, and then you can turn angles. And if you set up your transit here, you can calculate pretty quickly what each turn is, and then you tell your field guy where to put the stakes, and then you turn the next angle. Two guys pull out the 100-foot long cord, and then they set a stake. They pull out the 100-foot long cord. This guy turns the angle, tells them where to line it up. Boop, they set the stake right through that. And that is how you laid out those curves. And like I say, very quick. They had to keep ahead of the track crew coming behind them, so they didn't have much time to think about it. There's another view, same kind of idea. This is from a Hickerson book, by the way, which if you ever want really detailed instructions on how to calculate anything in the surveying side of it and layout and geometry, then Hickerson is the right book to get. It's a little tiny book and maybe out of print now, but it's the geometric Bible of highway and route design. And so there you go. Plug for Hickerson. Thank you, Hickerson. So this is measuring along, if in a single 100-foot arc, they're using, in this case, D, which later on we're going to use it for degree of curve. So don't get confused. This is the angle that you would turn within a 100-foot arc. And they're just showing you how the layout is. If you stood here and then measured over this and measured along the arc 100 feet, and then if you had the transit here, you would turn half of whatever this angle is, and that would line you up, and then you could tell them where to put the stake. All right, in a chord definition, now this dotted line is the 100 feet long piece, all right, through here, and this included angle down here, D included angle, is through there. Now you would measure that angle. You're laying out a railroad in the chord definition. You're here. You turn half of this included angle based on this definition, and then your buddies pull a 100-foot string exactly along the line that you're looking at. Set the next stake, and so forth, right around the curve you go. Right, so that's chord definition, 100 feet along this. Arc definition is 100 feet along here. The included angle is different, and so you'd have a different included angle depending on which definition you've got. I think a 100-foot chord is, well, it depends on the radius, right? A 100-foot chord, it's like 100.1 feet along the arc sometimes. You know, these are pretty gentle curves. We don't do them that, they're not that tight a curve. Horizontal curves, here's our radius, right? We've got, so whatever radius we can calculate, if we know what our degree of curve is. Right? In highway design, we lay everything out by radius. We put this on the plans R. We're going to build everything off radius. In railroads, we do everything by degree of curve, and so that's D. And so we say in each 100 feet, so back here, each 100 feet of chord, right? How many? If your vehicle was here and you were aimed this direction, how much change in angle is the bearing, which direction your vehicle is aiming by the time it gets down here? Right, that's the degree of curve, which in this case maybe D is inaccurate. It's not accurate for arc, but it is accurate. Your degree of curve is accurate here. That's the degree of angle change that your vehicle has faced as it goes through 100 feet of chord distance. Right, so that's our D, and so that's a 1 degree curve. A degree of curve of 1 means that every 100 feet, the direction your vehicle is headed in changes 1 degree. If I was going due north after 100 feet chord length, my vehicle would now be going, if due north is 0 degrees, I would now be going 1 degrees to the east of that. And after another 100 feet, I'd be going 2 degrees east of north. And after 300 feet, I'd be going 3 degrees east of north, right? See? So that's the degree of curve. So that's how much the angle of your vehicle changes for each 100 feet of chord length in this railroad definition, right? Or that. And so here's our equations. If you want to calculate the tangent length, which is this guy, here's D is the degree of curve, and delta is the total change in bearing that you want to do at your PI. So if I come up here, I need to turn 10 degrees to miss something. All right, my delta would be 10. If I divide it by L times 100, that would be my degree of curve. Right? So it's, again, look how easy this equation is. So if you're laying this out in field, it'd be really quick to calculate what your degree of curve is. Okay, all right, I need to turn 12 degrees, and I only want to do a 1 degree curve. All right, I need a 1,200 foot long curve. Bam, there you go. All right, now it gets a little more complicated because they put spirals on the ends of these later, but okay. And if you want to calculate the radius, if you were actually going to lay this out and find your center point and all that, there's the equation to find the radius based on the chord definition, right, through this. Now, in railroads, we always have a spiral, and so remember that every track, okay, maybe not the 5 mile an hour one, but every other track, any mainline track you've got is going to have a spiral for it. And roads, we don't have to have spirals. We can, but we don't have to. And this would be how this would, we'd put this together. And we've blown up the spiral so you can see them easier. Sometimes the spiral is only a small piece of the arc, the total curve. Sometimes it's a bigger piece. All right, and so we looked at these briefly when we did horizontal design before. So here's our spiral links in the red. All right, and these are a large portion of the total curving here, and this blue portion in the middle would be the arc, where you're at a standard radius arc through this, and so the radius doesn't change. Here's our R during the curve, and then here's this part is changing in radius as it moves. It starts at infinite radius here and comes down to a fixed radius, which matches the blue side, and then that. So here's tangent to spiral, spiral to curve, curve to spiral, and then spiral to tangent down there. So there's our curve and our arc sections. We're always going to have spirals on railroads. So let's keep that in mind. Here's our railroad design. What's our super elevation rate need to be, right? We're going to super elevate these tracks because it's just like highways that we have centrifugal force pushing out. This is on the northeast corridor through there. So we've got three different types of passenger trains going here. This one's coming out, that one's leaving, going away, and here's a commuter rail line coming in. I think this is in Pennsylvania. SEPTA, I think, is near Philadelphia, isn't it? So, but here's, you can kind of see they're all tilting, right? That's that super elevation, which we've already done this in highway. We can do it in railroad too. And this is the equation. And the difference here is we measure super elevation now in inches. This is a big deal. We measure it in inches. We don't measure it in percentage like we do highways. It's in inches. And so whatever the inch difference is, and you can see down, thanks to Wikipedia, you can see we've got this little measuring gauge. There's a level right here to make sure this crossbar is level. And on this side, this is all graduated. It shows you how many inches off of the level line from the other rail down to this rail. Right. So this would be the low side of the track, the high side of the track. You can measure what that super elevation is, and we measure it in inches. Why do we measure it in inches? That's because in highways we do it in percentage because the width of our road changes. And so a percent is a good way to reference it. In railroads, their width had better not change. They have a standard gauge here, 4 feet, 8.5 inches. That should not change. If it does, trains fall off the tracks. It's not great. So we just measure it in a fixed value, right? An actual value, and not as a percentage. And so they measure it in inches because that's what they were laying everything out as, right? So if you're laying this track out in the field, you've got a 100-foot long cord, you got this guy, and you say, well, I need 2 inches of super elevation, right? Pop this on here, set it to 2. You can change pretty easily the elevation on track because you just adjust the ballast under it. Now, even by hand methods, it can be done. Well, you need a crew more for that. Nowadays, it's all automated through there. But yeah, it's pretty easy to lay this out, right? And you can adjust that super elevation. So that's what we're looking at. This is the actual elevation. This is what you're measuring with this guy over here. And this is what? So it's 5 inches. So you'd plug 5 in here plus 3. This times divided by this. D is your degree of curve. So we're back to the degree of curve. See how easy this is. All right, take the square root, and that is our maximum velocity then. All right, through that. Yep. So that's super elevation. Now if we go over here, we do all of our super elevation development. We go from 0 super elevation up to whatever it is during the spiral. We like to do it all during the spiral. All right, if we come back to here, we start here, we have 0 super elevation. As we come into the curve, now we're at full super. We maintain that full super through the curve, and then we slack it off again over here and back to 0 and back on the tangent. All right, so the curve length exactly matches the distance you need to develop super elevation. And that's important, right? In highways, we didn't do it that way. Remember, we put like 20 to 25% of the super elevation came after the point of curve, right? And we did the rest before, so it was a little bit unbalanced there near the point of curvature as we come through. So it's a little weird, but in railroads, it's more perfectly matched. So the spiral length is equal to the distance you need to develop your super elevation. All right, for that. And so because of that, we've got these two equations, and this is the unbalanced amount of super elevation, and this would be the actual super elevation. We have two different length options to use, and we use whichever one is bigger. So we're going to use whichever L is longer in this. So super elevation, this is EA, is the actual measured super elevation. Unbalanced is, like even in highway curves, right? As you go around a curve, you can still feel being pushed outward in the car, right? You're kind of probably, if it was exactly balanced, you wouldn't feel it at all. You're like, I didn't even know I was on a curve. It's perfectly balanced, right? You'd be sitting, you wouldn't feel any external force pushing you to a side in a car if it was exactly balanced. And that's great, but that only works for exactly one speed at exactly one super elevation. What in railroads, what they say is, well, you can have some still force pushing you out. They call it the unbalanced elevation, and it's still in inches. And what they calculated is they say, well, it's typically 3 is the normal, would be a normal unbalanced elevation. Now for some railroads, different uses, you may use a smaller unbalanced elevation, but you shouldn't get tipping, right? Most things are designed for up to 3 unbalanced inches. And so if you only needed 3 inches, you could leave the track flat and have 0 super elevation. Yes, you'd feel like you were being pushed to the outside as you go through the curve, but not beyond what the trains can handle and you. And so this is the unbalanced, and that is anything that isn't exactly balanced at what you're doing, right? So, and then this is a 62. This is the actual super elevation in inches. So these are in inches, E's are in inches, V is in miles per hour. And this is just some conversion factor to convert everything together to give you feet. So anyway, the equation is self-correcting. It's kind of like the rational method, right? It just magically comes out in CFS. This magically comes out in feet. Okay, it's all built into this 1.63 or there, and this one's 62 is building that in, right, for that. So that's how we would calculate our spiral length needed. Whichever one's bigger is what we're going to use, and we're going to develop all of our actual super elevation during that spiral. Even if you don't need super elevation at all, you're still going to use one of these 2 numbers, right? You're still going to have a spiral, even if you don't need super elevation for it, if it's a very low, gentle curve, right? Vertical curves, this is the equation for vertical curves. Our L is equal to D times V squared times K, all over the algebraic, or I'm going to say this is algebraic difference. It is not. In railroads, this is the vertical acceleration. And in freight, it's a very gentle crest and sag curves. They use it for both. This length of curve is based on both. All right, we based our length of curve on stopping sight distance, mostly. And there's some other limits to it too, but most of ours in highways was stopping sight distance. In passenger trains and in freight trains, it's some acceleration rate, feet per second squared, right? It's some feeling of acceleration. Now, passenger trains can handle better. Freight, you gotta be really gentle on freight trains. It's not that, maybe we're a little worried about jostling freight, but not much. It's more that this is so hard for a freight train to pull cars through over the top of a hill or back up the other side of the hill and through the curve. They want it to be very gentle. And so that's how we're dividing that through there. So this is our difference. And this is what we would have called A in the highway stuff, the algebraic difference. Our D is if you came in at 2%, out at 2%, our D would be 4. So you'd plug in 4 here. That's our algebraic difference in grades. Here's our V squared in miles per hour. K is just a conversion factor, 2.15. Just plug that in. And then here's our acceleration feet squared, all right, for that. Right, so that's how we would calculate the length of curve we need in vertical curves. All right, so let's do an example. Let's do the horizontal example. So we've got a bearing of horizontal alignment changes. So in this delta, this change up here, I want 5.5 degrees. This PI, I need that for whatever I'm trying to line up with my railroad design. And I don't want to go over a maximum of a 1 degree curve. That's not uncommon if you've got it. All right, railroads like to be very gentle on this. So a 1 degree curve, fine. And what's my length of curve need? What's the length of the curve going to be here in the chord definition? And what's the radius going to be? So degree of curve, remember this equation, we reordered that, put L over here. L is going to be, here's my degree of curve, my delta, my change in angle divided by degree of curve, I get 550 feet. All right, you probably saw that coming at 1 degree curve. So you can only change 1 degree per 100 feet times a total need of change of 5.5, 550 feet. All right, we can calculate the matching radius for that would be 5,729. Great. All right, but now what's my super elevation needed? All right, so if I'm going to say that I want to design for a 70 mile per hour, it's going to be a passenger train, right? So 70 mile per hour train coming through here, what super elevation do I need? So here, reorder this equation, I get this. Here's my degree of curve. Here's my unbalanced inches. Maybe I don't want to use full 3. Maybe I want make people feel more comfortable going high speeds. Maybe I want to use a 1 here, right? But we're going to use 3 because that's our standard here. We plug this in. V squared is in miles per hour. Degree of curve, unbalanced in inches. I only need to super elevate another 0.43 inches. A 1 degree curve is really gentle. right? So now I know what my actual super elevation is, E sub A. Now I can use these two equations. E sub A, plug this in here. Here's my 0.43, right? I only need a 27-foot long spiral to develop that much, to develop less than half an inch of super elevation. Okay, that's one number, and then I had to check the other one. And this is my unbalanced curve. So this is, this is unbalanced forces pushing you out. The greater this unbalanced is, the more gentle you want the spiral leading into the curve to be, I think, so it doesn't jerk you around and scare everybody and create dynamic forces within the terrain. So here's this equation is using the unbalanced piece, 3 inches of unbalanced times, oh, this is wrong. It should be 70. Here, this should be 70, sorry. I started at 60 and then I changed it because it didn't look like a good enough number. That should be 70. You'll get an even longer, so you can have really long spirals through this. And it's only a 550-foot curve. You're going to get really long spirals either side of it to very gently move you into this unbalanced condition as you go around the curve. Right. Last thing is, you follow this link, it's in the notes. You can watch how they actually do track construction. That kind of completes the first section from today of the track piece. Next time we'll be picking up on traffic calming.